the focus of this talk is actually on a very new insight that we've gotten that actually combines technology from distributed simulation and real-time systems. So I think it really fits the conference extremely well. If you would like to learn more about it, then there is an archive paper, which you can find the reference to here. And I assume we will make these slides available, so it'll make it easy to find. But if you just go to my website, it's not that hard to find. So, okay, the talk starts from a classic result due to Eric Brewer, who is a colleague of mine at Berkeley and is also at Google. In the year 2000, at the Principles of Distributed Computation conference, Eric Brewer gave a keynote talk in which he kind of upended a lot of the work in distributed databases by asserting that it was impossible to maintain both consistency and availability in the presence of network partitions. And this became known as the CAP Theorem. At the time that Eric presented it, it was really a conjecture. He didn't have a proof of it, but it was later proved. And the key notion is that a lot of the goals in distributed systems that we, I think, all naively had, which was essentially that they would behave the same way as localized computational systems, that's actually unachievable. So it's a very fundamental result. And I'm going to talk about some applications of this idea and this limitation to cyber-physical systems in particular. So first of all, let me explain the CAP theorem. So if you have a distributed software system, so you've got software components that are communicating over a network, and they share variables, so they have replicas of some variable x, then consistency is simply agreement on the values of those shared variables. So in the database context, for example, this would be a distributed database with replicated data, and you want the software components to agree on the value of a record in the database. Availability is the ability to respond to reads and writes that access those shared variables. So if you have users accessing your database, for example, you'd like them to be able to read the value of a variable, and ideally they just use the local replica so that you don't incur the network latency, and you're tolerant to network partitions, and you can provide the value of the variable even if your network has temporarily failed. So the CAP theorem says that if your network fails, then you cannot have both of these properties, consistency and availability. And that's a pretty intuitive idea, right? Because obviously if you break the network here and you update the variable x in one of these software components, the other software component is not going to know anything about that update, and so consistency becomes impossible. But this trade-off turns out to be really quite a bit more subtle. Now, I'd like to extend this theorem to cyber-physical systems where the software components are interacting with a physical plant. And here, consistency is not just about the value of shared variables, but also about the view that the software components have of the physical plant. They have some notion of what the state of the world is. And what I mean by consistency here is that their view of the state of the world is the same. Okay? So the CAP theorem is going to tell us that the ability to maintain that consistent view of the physical world and maintain availability turns out to be impossible. So let's look at a very specific example. So this is braking assistance that is a fairly common part of advanced driver assistance systems, or ADAS systems. So at the upper right is an image from a Denso demo in October of 2018 of such an ADAS system where a camera detects pedestrians and automatically applies braking. So a software architecture for this looks like what you see down in the lower left, where you've got a camera, and then the braking assistant is a software component that does analysis of the images and detects pedestrians. And then if it detects a pedestrian in front of the vehicle, it'll issue a signal to the braking system to apply the brakes. But of course, you also still have a brake pedal, so the brake pedal will also issue commands to the brake subsystem to apply the brakes. By the way, all of the software that I'll show here is actually realized in this Lingua Franca language that Libero kindly mentioned in the introduction briefly. So this image is actually automatically generated from a Lingua Franca program. So let's have a close look at this very simple software system. So assume that the camera takes an image, a snapshot, at some physical time, capital T. The braking assistant is a software component that does some image analysis on this. It may be a fairly complex software component, and so it may take quite a bit of time to execute, but its result is still about the state of the world at this time T. And so the braking assistant we think of then as logically instantaneous because its result is about the state of the world at the time that the snapshot was taken. Okay? Now, suppose that the brake pedal issues a command ever so slightly later than time t. So t plus epsilon. The brake pedal issues a command. The question then becomes, should the brake component wait for the analysis of the braking assistant before responding to the brake pedal? So keep in mind that the braking assistant is an image analysis program, maybe a machine learning engine that is detecting pedestrians. It may take quite a few milliseconds to complete its execution. And the question is, should we delay the response to the brake pedal command waiting for the result of the braking assistant? So if your answer is yes, you are emphasizing consistency. In other words, the brake subsystem needs to have a consistent view of the physical world, meaning that it needs to know the state of the world at time t before it reacts to the state of the world at time t plus epsilon. Okay? That's emphasizing consistency. On the other hand, if you emphasize availability, then the answer is no. The brake component should not wait for the analysis of the braking assistant before responding to the brake pedal. Okay? Now, this is not necessarily a networked system. Here I've talked about simply the braking assistant's computation time. But computation time and network latency turn out to be indistinguishable in this CAP formalism. And so you could replace this with a networked system, in which case network latency would become the issue. But you don't even need a networked system for the CAP theorem to kick in. It's already sufficient to be talking about execution time. All right? This particular application emphasizes that your choice between consistency and availability is very application dependent. In fact, in particular, I would argue that for this braking assistant, you want availability. You don't want consistency. If the brake pedal gets pushed, you want to respond immediately, regardless of whether the braking assistant has finished its computation on some snapshot of the physical world. But that's an application-specific choice. And here's a different application, this one due to Ravi Akella at Denso, where the answer is the opposite. You want to emphasize consistency. So this is a four-way stop intersection. This is an aerial view in the Carla simulator. The particular simulation here was built by Soroush Bateni of UT Dallas, who integrated Carla with our Lingua Franca language so that you could build these kinds of simulations. And you can have some number of vehicles interacting with this intersection. And in this particular design, there's a roadside unit that is mediating access to the intersection. Now, the question is, in this particular application, do you want to emphasize consistency or availability in the presence of network partitioning? And I would argue that in this particular application, you want to emphasize consistency. You want agreement among all the vehicles about the state of the intersection. You don't want two vehicles to simultaneously think that the intersection is available to them, because those two vehicles will then enter the intersection and a collision will result. So availability here is the ability to enter an intersection. Consistency is agreement on the state of the intersection. And for this application, you want a design that emphasizes consistency over availability in the presence of network partitioning. So the choice between consistency and availability is forced upon you. If you have a networked system, or if you have non-trivial execution times, you will always have to make this choice between consistency and availability. It's not an option. So the shared view of the system is an essential part of having availability. If you're going to be talking about availability at all in the presence of network partitioning, then you need to have replicated data. Okay, so let's assume henceforth that our software components have replicated information about either the physical plant or some variable in the software. So suppose, furthermore, that updates can occur in multiple places. So the shared variables, which may be derived from sensors that are reading the state of the physical plant, or they may be users interacting with the system in the context of a database system. It might be somebody updating a record. The updates can occur in a distributed fashion, and the updates need to be propagated through the network then in order for there to be some sense of consistency here. Okay, so consistency, in fact, requires agreement on the order of these updates. So if you have two updates occurring to a variable, update 1 and update 2, you're going to need to put these in some order normally. Now, there's ways, for example, in database systems to mitigate that requirement. So, for example, if your update operation is commutative, so, for example, you just add a value to a variable, and you're not using floating point arithmetic, you're using integer arithmetic, and you're handling overflow and so forth. So the updates are in fact commutative. Then the order can be relaxed a bit, and you do eventually get consistency once you propagate the updates. But in most applications, you don't actually have commutative updates, and consequently, in order to have consistency, you're going to require agreement on the order of the updates. So the software components have to know which update occurred before which other update. Now, you might naively think, well, you should just use physical time, right? If update 1 occurred in physical time earlier than update 2, then the semantics of your system should treat update 1 as occurring before update 2, and consequently update 2 will overwrite the value of update 1, and consistency will mean that all software components agree that the final value is the one delivered by update 2. But the problem with that naive notion is that we don't actually have access to that ideal Newtonian time that tells us whether update 1 occurred before update 2. In fact, from the theory of relativity in physics, if these software components are separated in space, then it becomes impossible, if the updates are close enough in time, to determine which update occurred before the other. In fact, it becomes an ill-posed question which update occurred before the other, because it could be dependent on your frame of reference. So the reality is that in any system, you're going to have to work with some imperfect measurement of time. So let's assume that each software component has access to a local physical clock, and that these clocks are kept in some measure of synchrony. So, for example, you might be using the network time protocol, NTP, or you might be using the more precise mechanisms that are available today, the precision time protocols, PTP. But you have clocks that have some agreement about what the local time is, and then when an update occurs, you use those local clocks to assign a timestamp to these updates. Once you've assigned a timestamp, that timestamp becomes a number, and you can define the semantics of the system to be dependent on those numbers. So if update 1 gets assigned a timestamp that is earlier than update 2, then semantically you treat update 1 as having occurred before update 2, regardless of whether in some physical sense it actually occurred earlier. So that's a fairly common way to deal with this notion of consistency in a distributed system. So with imperfect clock synchronization, you can use physical time to assign a logical time to the system. Okay, so let's assume that we're doing that. And update 1 occurs at some time T1, update 2 occurs at some time T2. These times are drawn from local clocks. Then the order of the updates will be determined by the numerical order that are assigned to these timestamps. So let's go back to our breaking assistant and use these timestamps. So the snapshot assigned to the camera is some logical time now, T1, drawn from some physical clock. Okay? We have a logically instantaneous operation. It's logically instantaneous because the result of the operation is telling us about the state of the physical world at that same physical time based on the local clock. So the timestamp is still T1. The timestamp of the brake pedal is some T2, where T2 is drawn from a local clock. And so consistency requires that the brake component see events in timestamp order. If we want to enforce consistency here, that's going to reduce availability. Depending on the execution time of the braking assistant, it means that if a brake pedal gets assigned a logical time that is slightly greater than the logical time of the snapshot, consistency requires that the braking system see the events in timestamp order, so enforcing consistency will reduce availability. So that's not surprising. The CAP theorem tells us that this trade-off is inevitable. Now, the new result, the one that is in this archive paper, not yet published, generalizes the CAP theorem and quantifies this result. So it assigns numerical values to unavailability. It turns out to be more convenient to talk about unavailability than availability. And it assigns numerical values to inconsistency. And then it derives a algebraic relationship between unavailability and inconsistency. And the algebraic relationship is shown here, and I'm not going to go through the mathematical formulation. I'm going to focus on the intuition. So let me just tell you what the CAL theorem says in words. So it says unavailability is the larger of two quantities. The first one is a local processing offset needed to ensure that timestamps are processed in order. Okay, this is defining a semantic notion of consistency. It's using timestamps to define the order in which things get processed. Or the apparent latency, which is a quantity that is defined in this paper, minus the tolerance for inconsistency. Okay, and apparent latency is the sum of four quantities: processing offsets, network latency, clock synchronization error, and execution time overhead. And one of the claims in this paper is that, in fact, you can't tell the difference between network latency, clock synchronization error, and execution time. Those three quantities are indistinguishable from one another. The paper derives a very elegant max plus formulation that shows where all of the quantities A and gamma and O and the identity matrix I, these are all matrices in this case, but in the max plus formulation, it shows that unavailability is in fact a very simple linear function of these processing offsets. So the math is subtle. The intuition, however, is fairly straightforward, and I would like to illustrate the intuition for you using the Lingua Franca framework. So I need to tell you a little bit about Lingua Franca because probably most of you have not encountered it yet. So it's a collaborative effort that is, the main developers are in Berkeley, Dallas, Dresden, and Kiel. So it's mostly a German-US partnership that is developing this framework, and it's what we call a polyglot meta-language. So it's not a programming language, it's a coordination language. The logic of programs is written in a language that you choose, and we currently have support for, 4.5 languages. So C, C++, Python, TypeScript, and Rust is progressing very nicely. Pretty soon, full support for 5 languages, but Rust is not quite complete yet. So this particular language uses timestamps in a way that is very familiar to people who are familiar with discrete event simulators, so such as the ones you might find in Ptolemy 2, or in the high-level architecture, or in devs systems, or in hardware simulation languages like Verilog and VHDL. So events are timestamped, and the semantics of the language is that events get processed in timestamp order. The language also borrows key principles from synchronous languages in that, by default, executions of reactions are logically instantaneous. And so it has a fixed point semantics similar to synchronous languages. It also borrows concepts from actor languages. So the concurrency model is similar to actor languages, but more deterministic because of the use of timestamps. So in the context of this language, here's a little snippet of code in the language where you define a reaction to some event, and the body of the reaction is delimited by this funny delimiter, this curly bracket equals, and the body of the reaction is written in your target language code. So in this particular case, this is C code in the body of the reaction. But the component architecture, the stitching together of these pieces of C code, is done using the Lingua Franca framework. And here you can see a reactor that is implementing a small test system called a reflex game that instantiates 2 reactors, one called random source, one called get user input, and then connects the ports of these components. Ports communicate timestamped events between the components. So that's a little snapshot of the Lingua Franca language. Let's look at what this car braking example looks like in a little more detail in Lingua Franca. And in particular, what I'd like to do is show you how you can specifically and explicitly explore the trade-offs between consistency and availability. Okay, so in particular, suppose that I put a logical delay of 10 milliseconds between this braking assistant and the braking subsystem. Okay, what does that mean, to put a logical delay in there? What it means explicitly, I am stating that the braking subsystem can tolerate inconsistency up to 10 milliseconds. In other words, it's okay for this braking system to see slightly stale data from the braking assistant. It's 10 milliseconds old compared to the physical world. Okay? What are the consequences of tolerating that increased inconsistency? Well, in this particular application, what this does is this converts this system into one that is effectively using what Tom Hensinger called, way back in the early 2000s, the logical execution time principle. And he showed that this was a very good way to get deterministic concurrency in cyber-physical systems. Okay? Introducing this logical delay is a one-line change in the Lingua Franca program. When you connect the vision output port to the braking subsystem's input port, you just specify a logical delay using this after keyword, after 10 milliseconds. Okay, so let's look at what this does to the timestamps. So if the camera issues a snapshot with timestamp T1, the braking system will see a timestamp of T1 plus 10 milliseconds. It's that simple, okay? But the consequence of this is that the braking system, the braking subsystem, can advance its notion of logical time 10 milliseconds ahead of vision and still maintain the property that it is operating on events in timestamp order. So it turns out that if the execution time of the breaking assistant plus the network latency, if this is a networked communication, if those are less than 10 milliseconds, then the unavailability of responses to the brake pedal reduces to 0. You can respond instantaneously to the brake pedal regardless of how long the braking assistant is actually taking to execute. So we get an inconsistency tolerance of 10 milliseconds and an unavailability of 0 if the braking assistant execution time and the network latency is less than 10 milliseconds. Okay? So this is effectively the logical execution time principle, and it shows that we can use this to explore the trade-offs between consistency and availability. Now, it turns out that what if your execution time isn't bounded by 10 milliseconds? Suppose that in fact, maybe it's a networked communication and maybe the network gets broken, okay? In which case, 10 milliseconds may be unrealistic. Well, in Lingua Franca, another one-line change, changing the connection between the vision subsystem and the braking system to what we call a physical connection, reduces the unavailability to 0 regardless of execution time and network latencies now. So the braking system will be able to respond instantaneously to the brake pedal regardless of execution times. But the cost of this now is that the inconsistency is unbounded. So the way that this works is very simply that a physical connection, which is denoted in this graphical rendition by this little squiggly line, assigns a new timestamp at the receiving end based on the local clock. So what that means is that the timestamp of the received result of the braking assistant, all we know is that it's later than the occurrence in the physical world, but we don't know by how much. So the inconsistency becomes unbounded, but now the unavailability is guaranteed to be 0. So let's look at the more optimistic case where you set the logical execution time to 10 milliseconds and you hope that the braking assistant will in fact, the braking assistant's execution time plus the network latency will be less than 10 milliseconds. What if it isn't? Okay. Well, what the CAP theorem tells us and the CAL theorem quantifies is that we are forced to make a choice. We have to make a choice here. We have to make a choice to either sacrifice availability or sacrifice consistency. You cannot get away with not doing one or the other. So in other words, if the execution time bound is violated, the braking subsystem either has to wait until the network gets repaired or the computation finishes, in which case you've sacrificed availability, or it has to proceed and process the brake pedal signal, in which case you sacrifice consistency. You have to do one or the other. Now here, I would like to particularly credit Soroush Bateni of UT Dallas because he is really, more than anyone, the one who really made this a reality in Lingua Franca, because he built these two coordination mechanisms in Lingua Franca that give you a choice. You can either sacrifice availability or sacrifice consistency, depending on which of these two coordination mechanisms you pick. So centralized coordination extends methods used in distributed discrete event simulation. So if you're familiar with distributed discrete event simulation, such as the high-level architecture or DEV systems or distributed hardware simulation techniques, the methods that are used there, they emphasize consistency. Simulation requires you to process things in timestamp order, irrespective of network latencies, otherwise your simulation becomes invalid. So it's kind of natural that you would use these kinds of techniques if your focus is on consistency and you're willing to sacrifice availability. So in this particular case, there's a runtime infrastructure that mediates the time advance in each of the components. Alternatively, if you need availability over consistency, you can use decentralized coordination. And this technique extends methods that are used in distributed databases, such as the TIDES technique, which was developed in my group 14 years ago, and Google Spanner, which is a global distributed database at Google. And this is a technique that uses clock synchronization to coordinate a distributed system with timestamps. So let me give you a sense of how this works. So assume that you have now a networked system with centralized coordination. Okay, so the vision system is running on one microprocessor, the braking system is running on another microprocessor, and there's a network communicating between the two, and we've specified in the program a 10 millisecond bound on inconsistency. Okay, that's what this after 10 milliseconds does, is it specifies our tolerance for inconsistency in the program. So now, if the execution time actually violates that 10 millisecond bound, or the network gets broken, so the message doesn't arrive at the braking system within 10 milliseconds, then the runtime infrastructure in centralized coordination will block the advancement of logical time at the braking system. Okay? This is enforcing consistency over availability. By blocking the advancement of time, it will block responses to the brake pedal at other larger timestamps until it has actually, the network has gotten repaired and it receives the message from the braking assistant. Now, of course, for this particular application, as I emphasized before, that's actually a pretty poor choice. You don't want centralized coordination for this application because you really need availability for this application. But for the four-way intersection example, you want the reverse, so both are useful. So for this particular application, you would be better off choosing the decentralized coordination. And decentralized coordination enforces zero unavailability, exactly zero, okay? So we've specified our tolerance for inconsistency to be 10 milliseconds. If the vision system takes more than 10 milliseconds to execute, or the network takes more than 10 milliseconds to deliver the message, the braking system will nonetheless proceed and advance its logical time, okay? So we'll sacrifice consistency because if we then later get a message from the vision system that got delayed in the network, that message will have a timestamp that is now earlier than the logical time at the braking system, and therefore will violate the timestamp ordering. We've sacrificed consistency in order to maintain availability. So in particular, using the CAP Theorem, you can derive exactly what the braking system needs to do. When the brake pedal produces an event with timestamp T1, the braking system should process it when its local clock exceeds the value of that timestamp T1 plus the network latency plus a bound on the clock synchronization error plus the execution time overhead minus the 10 millisecond tolerance for inconsistency. Notice here that if the network latency plus clock synchronization error plus execution time is less than 10 milliseconds, then the braking system has exactly zero unavailability. Exactly zero, because it can process the brake pedal event as soon as its physical clock matches the timestamp, and the timestamp was assigned using that same physical clock. Therefore, unavailability goes to zero. The braking system can respond immediately to the brake pedal. And if it does, in fact, if the braking system, the braking assistant and the network latency are in fact less than 10 milliseconds, then the program will behave deterministically exactly as specified with this 10 millisecond tolerance for inconsistency. Now, of course, things can go wrong. The network could break and messages could arrive out of order. In Lingua Franca, this is a detectable fault, in fact. If you receive an event with a timestamp that is too stale compared to your assumptions, then the Lingua Franca programming framework allows you to specify a reaction to invoke to respond to that fault, to handle that fault condition, because it's no longer possible to maintain the semantics that are defined by the timestamp, and so you have to respond to that using a fault condition. So let me look at a little bit more challenging example. So this is one where you actually have distributed updates, and you have distributed replicas of the data. So this is an actual Lingua Franca program that you can read about in full detail. The full source code for this is given in this archive paper. So you've got a user input where a physical action here in Lingua Franca generates asynchronous events and assigns timestamps based on the local physical clock. The syntax of Lingua Franca allows you to very compactly create some number n of these user inputs. So you can have a distributed system. So let me give you a concrete application that fits within this framework. Suppose you have ATM machines. So these are automatic teller machines that dispense cash, all right? And they're distributed across the network. There's n of them. And users walk up to the ATM and want to withdraw cash. And the bank would like to dispense the cash only if the bank balance is sufficient to allow for the cash to be dispensed. So you need the bank balance to exceed the amount of the requested cash. So suppose that the ATM machines each keep a local copy of the bank balance. So that's the replicated data. And the question now becomes, do you want to emphasize availability, which means that the ATM can respond using its local copy of the bank balance immediately, okay, regardless of what's going on in the rest of the system? Or do you want to emphasize consistency, which means that all of the ATMs will need to agree on the bank balance, and you want to guarantee that before an ATM distributes cash, that it uses the agreed upon value of the bank balance before dispensing the cash? That's a business decision, which of those two you want to emphasize. And my guess is that for this particular application, you want a balance between them, okay? You probably want, the bank is probably willing to take some risk, and so it's willing to tolerate some inconsistency in order to have good availability, even if networks become partitioned or network latency becomes large. Okay, so this Lingua Franca program can be used to build that application. So in each of these ATMs, each time a user goes to ask for the bank balance or request a withdrawal, a timestamp gets assigned to that request based on the local physical clock, and that timestamp gets broadcast to all of the other replicas. So this last line of code, u.update plus, goes to r.updates, broadcasts the updates from each of the user inputs to all of the replicas. And that's shown in this bold connection here. So the bank of replicas will receive updates from all of the user inputs. In addition, there is a local loop where when a request occurs and gets assigned a timestamp at one of the local ATMs, there will be a response that tells the user what the current bank balance is, okay? And that's this query input to the local replica, which provides the response. Okay, now, in this particular Lingua Franca design, we've emphasized consistency. So in particular, there's no after delays in these updates or in fact anywhere in this loop. And as a consequence, one other thing is that in Lingua Franca, if you have two reactions, these little chevrons represent reactions, which are chunks of application code that get invoked. If you have two reactions within the same reactor, and you have inputs that with simultaneous timestamps, those will be invoked in the order that they're specified. And as a consequence, at each timestamp, the replica will receive all updates that have that timestamp or a lesser timestamp before it can respond to the query. Okay, so as a consequence, in this particular design, the response will always be the global consensus on what the bank balance is. So there's no tolerance for inconsistency in this design. So enforcing this strong form of consistency can be done, again, in two ways. You can do it in such a way that you emphasize consistency over availability, in which case, if your network breaks, the runtime infrastructure will block progress at an ATM and prevent the ATM from dispensing cash or reporting the status of the bank balance until the network gets repaired. That's a choice. And that's what centralized coordination in the Lingua Franca program will do. It'll implement that choice. Interestingly, the standard methods from distributed discrete event simulation actually can't realize this. They can't handle these zero delay loops. If you look at the standard methods such as in HLA, the high-level architecture, or in DEVs, all of those standard methods require some logical delay in these feedback loops. In HLA, it's called a look-ahead delay. And so we had to extend these methods, and we found a way to do that. So in particular, the standard methods use a technique that is a time advance grant, where the runtime infrastructure assures each component that it has all inputs with tags T or less. We extended that with what we call a provisional time advance grant, which is very subtly different. It's where the RTI asserts to a component that it's seen all inputs with tags less than T, but not necessarily all inputs with tags equal to T. Okay? That very subtle difference enables execution of programs with these kind of zero delay loops, because if the user input here gets a P tag, a provisional time advance grant from the runtime infrastructure, then it will automatically block on this current value input before it'll block until it is assured that either that current value is that there is no forthcoming message with that timestamp, or it actually receives a message with the timestamp. And as a consequence, that blocking delivers this solution that emphasizes consistency over availability. Okay, the user input will block until it receives this input, blocking availability in order to maintain consistency. So the CAP theorem actually tells us in this case that the amount of unavailability here is, you can derive actually what it'll be, all right? And it's the sum of two communication latencies, clock synchronization error, and execution time overhead of some specific reactions that you can statically analyze the program to figure out which reactions you need to know the execution time for, and you can derive what the unavailability will be for this system. And if the network becomes partitioned, the unavailability becomes unbounded, as expected from the CAP theorem. If we choose decentralized coordination for this example, then we emphasize availability. But once again, we discovered that the standard method from our own previous technique, TIDES, and also in Google Spanner, is unable to handle these kinds of zero delay loops. This standard method uses a safe-to-process offset, where each software component can advance its notion of logical time when its physical clock reaches some threshold. But in our case, we've discovered that we had to actually extend this method in order to be able to handle these. And you can read about the details in this archive paper. So, summarizing what I've said. The CAP theorem tells us that network partitioning means you have to sacrifice consistency or availability. I'd like to emphasize that network partitioning, the choice of language suggests that the network breaks. But all networks have latency, and most networks have variable latency. And so network partitioning is not really a binary property. It's something that you can quantify. And so we generalize the CAP theorem to get a CAL theorem, where we replace partitioning with latency. The CAL theorem says that as network latency increases, or execution time increases because they're indistinguishable, or clock synchronization error increases because that's also indistinguishable, then either inconsistency or unavailability must increase. It's unavoidable. You have to choose whether inconsistency or unavailability should increase, and you get to do that in your design. If you choose centralized coordination, you will preserve consistency for all network latencies at a cost in availability. If you choose decentralized coordination, you will preserve availability for all network latencies at a cost in consistency. And in both cases, you can specify the acceptable cost in the Lingua Franca program. And then if that cost gets exceeded, then you can invoke a fault handler. Okay, you can specify the fault handler that will occur. So you make some assumptions about your network latency and your execution times, you build those assumptions into your program, and you put in fault handlers that get invoked if you violate those assumptions. So here is the reference again, and we'd love to get feedback from people. I think it's a rather beautiful result, and the fact that we're able to realize this trade-off explicitly in the Lingua Franca language was really quite a revelation to us and a really wonderful discovery. So thank you very much. And with that, I will stop sharing and open up for questions.